We're going to define this quantity y, which we will refer to as Young's modulus, as the ratio of the stress to the strain. In other words, the force per area divided by delta L over L naught. So what is y? What is Young's modulus telling us? It's telling us how the object or the material is going to respond for some applied force. What are the units of the Young's modulus? Well, that'll be the units of the stress. The units of the stress we saw were newtons per meter squared, divided by the units of the strain, and strain is unitless, so Young's modulus will have the same units as the stress, newtons per meter squared. So what is this telling us? It's basically telling us how much stress we would have to apply to an object per strain of 1. Well, a strain of 1 would mean what? The object would actually stretch so much that delta L was equal to L naught. In other words, it would have to double in length. Well, typically you're not going to be able to stretch something and actually double its length. The value of Young's modulus is really talking about material stretches that are relatively small compared to the overall size of the object. If I tried to stretch this rod to double its length, the aluminum, this is an aluminum rod, it would break. It would just snap in two. So the Young's modulus is really talking about values for small deformations, not large deformations. But back to what we're the comparison. The amount of stress per strain. The larger the value of y, the greater the stress that would have to be applied. So something that's very soft and can be stretched easily would have a small value of the Young's modulus. Something very stiff and hard that's very hard to stretch would have a much larger value of the Young's modulus. So let's keep in mind, large values mean something that's very rigid, very hard to change the shape, while small values of the Young's modulus, something that would be able to be stretched much more easily. Okay, great. Let's stick some numbers in here. So with our aluminum bar here, let's imagine that, well, again, we don't have to imagine. I actually took the measurements off the bar. Let's say we've got a bar of length 91.5 centimeters. And the cross-sectional area, I cut it across here. What's the area? Well, it's a circle with a radius of 2.50 centimeters. The area of a circle is pi r squared. So pi times 0.0250 squared is an area of 1.96 times 10 to the minus 3 square meters. The bar is aluminum, so it's got a Young's modulus of about 6.8 times 10 to the 10th newtons per meter squared. Notice that's a big number. It would take a whole lot of force to stretch this if you had a square meter of it. The stress, which is then the force per area, let's imagine that I pull on each end, right at the very, very end, I apply a force of, say, 10 newtons. That's between 2 and 3 pounds. That's not a very large force, but something we could definitely do with our hands, just pulling it apart like that. So what's the stress? The stress is the force per area, or 10 newtons, divided by the area that we had over here, 1.96 times 10 to the minus 3 meters. And that gives us a stress, a force per area, of 5,090 newtons per square meter. In other words, if we could take this bar and make it larger to have a cross-sectional area of 1 square meter, and we pulled 10 newtons on every little bit of it, this much, we would end up pulling with a force of 5,090 newtons for the entire square meter. Remember the Young's modulus we defined as the stress over the strain. The strain is then the stress divided by Young's modulus, which in this case gives us a strain of 5,090 newtons per square meter divided by Young's modulus, 6.8 times 10 to the 10th newtons per meter squared, which gives us a strain of 7.5 times 10 to the minus 8th. So how much would this thing actually stretch when I apply this force of 10 newtons? Well, remember the strain is equal to delta L over L naught, or delta L equals L naught times the strain times L naught, which is, the strain is 7.5 times 10 to the minus 8th times the initial length 0.915 meters, which gives us a change in the length of about 6.9 times 10 to the minus 8 meters, or about 0.068 microns, micrometers. That's a very, very small amount. So when I pull on this, do we notice the change in length? No, because we're talking about a very, very small change in length. And why is it such a small change in length? Because Young's modulus for aluminum is a very, very large number. Okay, great. Let's go on. Let's look at some other properties. What we've been looking at is basically when we try to stretch an object, and that depends on how much it stretches, is the tensile strength. And we were looking at the tensile Young's modulus. There's also a possibility that we could put the force to compress the object, and what we would get there is a measure of its compressive strength. For many materials, the tensile strength and the compressive strength are very similar to each other, at least for small stresses. There are some materials that have very different tensile and compressive strengths. For example, bone has a much higher compressive strength than tensile strength, because basically bones need to respond to muscles pulling on them, pulling them to tend to compress them, and they have much more strength that way than if you try to actually stretch a bone. It has a tendency to break more this way than if you try to compress it. Also, what if you push something to the side so that it deforms by kind of bending at an angle, so to speak? That's a measure of its shear strength. And the shear strength is also very similar, the same for many materials, to the torsion strength. So rather than just moving the top surface to the side, say, imagine you try to apply a torque and try to rotate it. How much will the material rotate? That's a measure of its torsion strength. So basically, these are all how solids respond to these various types of forces in different directions. How do liquids respond? They respond, as we've seen, in a very, very different way. Let's take a look at that next. So how do fluids respond to similar sorts of things as those properties that we just looked at with solids? Well, let's imagine we have a container of a fluid, something like maybe this beaker with water in it or something like that. While we saw it's hard to figure out how these fluids respond to changes in forces or having forces applied to the fluid, let's look at how the fluid exerts a force itself. Let's imagine that we have this container and we could make a little hole in the side of the container, and we put a little stopper in the hole. Well, that hole will exert a force on the stopper. So the fluid itself is now exerting the force. And we could imagine that the larger the stopper is, the more force the fluid is applying. So what we'll define is a quantity that's related to the force and the area of the stopper that we might use, or something like that. What we define is then the pressure, which is the force per area. So how much force is the fluid applying per area? And so we'll use a capital P to represent the pressure. Let's be careful, let's not confuse with the P for pressure with P for, where else have we used that? For momentum and power. So the pressure will be equal to the force per area. And this is going to be the standard way we'll look at pressures with fluids and how forces are being applied or applied to the fluids or by the fluids. So what are the units of pressure? Well, the standard SI unit for force will be a Newton. The standard SI unit for area will be a meter squared. And this is a combination that we will use often enough that it has its own name. 1 Newton per meter squared is called a Pascal, or capital P lowercase a. So we won't confuse this with the actual quantity pressure. The unit Pascal is a P, but with a lowercase a. So a Pascal is a Newton per meter squared. Now you might think about it, we are actually in a fluid right now, a gas fluid, which is the atmosphere, and at standard sea level, one standard pressure due to the atmosphere is called 1 atmosphere, 1 atm. That's an average atmospheric pressure due to being underneath all the fluid all the air, the fluid in our atmosphere. And this has a value of 101.325 kilopascals. In other words, 1.01325 times 10 to the 5th pascals. Okay, that is the pressure due to the atmosphere, on average, 1 atmosphere of pressure, 1.01325 times 10 to the 5th pascals. Okay, very good. Now, let's take a look at how this pressure actually varies depending on where you are in the fluid, if you're up near the top or down near the bottom. How does the pressure change? Let's take a look at that. Actually, sorry, before we move on to determining the pressure as it changes with depth, there is one thing I want to talk about first. Let's imagine we've got a fluid in a closed container, and I've got a piston here that can move up and down and change the volume or the size of the container where the fluid is. But let's imagine this whole container is filled with our fluid. And let's imagine there's some pressure acting on the fluid when the fluid has then some volume V. Let's imagine that we increase the pressure. We start pushing harder on the top. We push harder on the piston so that we increase the pressure by some amount delta P. So we now are pushing with an amount delta P. What do we expect to happen? Well, we expect that piston to drop down a certain amount, to move down, decreasing the volume. So we expect this piston to maybe move down some amount like this. Changing the volume so that our new volume is, let's say, some V plus delta V. But we know that delta V is going to be negative because the pressure, because the piston goes down, the volume decreases, so delta V will be some negative quantity. Well, the amount, the relationship between delta P and delta V has to do with the fluid, how compressible the fluid is. We will define this relationship of delta P divided by the relative change of the volume. In other words, delta V over, delta V over V. That's the relative change in the the volume, sorry. Now we know this is going to be a negative quantity, so this whole thing would be negative because we know, we expect delta V to be negative, so I'm going to put a negative sign out here just to make that a positive quantity. We will define this as a value that we will refer to as B, where B is called the bulk modulus. Modulus. So we've talked about these other moduli, the shear modulus, the tensile modulus, etc., Young's modulus for the solids. Here we have the bulk modulus for a fluid, and we can apply this for, we could use this with solids, but we can apply this with liquids or gases as well. So any kind of fluid, which relates basically how compressible it is. How much will it compress? The larger B, the less compressible the material is. The smaller B, the smaller B, the easier it is to compress, and the more it will compress. So if delta V is small, then B will be a large number, and if delta V is large, B will be a small number. So it measures basically the strength of the substance in its response to being compressed. Okay, very, very good. Let's now move on to looking at the change in the pressure in the, depending on how far down you go in the fluid.